Chapter 22, Section 2, Convection. Recall that heat transfer by conduction involves the transfer of energy from molecule to molecule. Energy moves from one place to another, but the molecules do not. Another means of heat transfer is by movement of the hotter substance. Air in contact with a hot stove ascends and warms the region above. Water heated in a boiler in the basement rises to warm the radiators in the upper floors. This is convection, where heating occurs by currents in a fluid. A simple demonstration illustrates the difference between conduction and convection. With a bit of steel wool, trap a piece of ice at the bottom of a test tube nearly filled with water. Hold the tube by the bottom with your bare hand and place the top in the flame of a Bunsen burner. The water at the top will come to a vigorous boil while the ice below remains unmelted. The hot water at the top is less dense and remains at the top. Any heat that reaches the ice must be transferred by conduction, and we see that water is a poor conductor of heat. If you repeat the experiment, only this time holding the test tube at the top by means of tongs and heating the water from below, while the ice floats at the surface, the ice will melt quickly. Heat gets to the top by convection, for the hot water rises to the surface, carrying its energy with it to the ice. Convection occurs in all fluids, whether liquid or gas. Whether we heat water in a pan or heat air in a room, the process is the same. When the fluid is heated, it expands, becomes less dense, and rises. Warm air or warm water rises for the same reason that a block of wood floats in water and a helium-filled balloon rises in air. In effect, convection is an application of Archimedes' principle, for the warmer fluid is buoyed up by a denser surrounding fluid. Cooler fluid then moves to the bottom, and the process continues. In this way, convection currents keep a fluid stirred up as it heats. Winds. Convection currents stirring the atmosphere produce winds. Some parts of Earth's surface absorb heat from the sun more readily than others. The uneven absorption causes uneven heating of the air near the surface and creates convection currents. This phenomenon is often evident at the seashore. In the daytime, the shore warms more easily than the water. Air over the shore rises and cooler air from above the water takes its place. The result is a sea breeze. At night, the process reverses as the shore cools off more quickly than the water. The warmer air is now over the sea. If you build a fire on the beach, you'll notice that the smoke sweeps inward in the day and seaward at night. Why rising warm air cools? Rising warm air, like a rising balloon, expands. Why? Because less atmospheric pressure squeezes on it at higher altitudes. As the air expands, it cools, just the opposite of what happens when air is compressed. If you've ever compressed air with a tire pump, you probably noticed that the air and pump become quite hot. The opposite happens when air expands. Expanding air cools. We can understand the cooling of expanding air by thinking of molecules of air as tiny balls bouncing against one another. Speed is picked up by a ball when it is hit by another ball that approaches with a greater speed. But when a ball collides with one that is receding, its rebound speed is reduced. It slows down. Likewise, for a ping pong ball moving toward a paddle, it picks up speed when it hits an approaching paddle, but loses speed when it hits a receding paddle. The same idea applies to a region of air that is expanding. Molecules collide on the average with more molecules that are receding than are approaching. Thus, in expanding air, the average speed of the molecules decreases and the air cools.